All right, today we are doing FTC part 2. We did part of it on Friday. Today, same concept, slightly different. Okay, let's look at it. We're evaluating the integral from 2 to x, 2x dx. It looks a little weird, but our rule's still the same. We are trying to evaluate a definite integral. So to do that, the first thing we're going to do is find the antiderivative of whatever's given. So Cannon, what's the antiderivative of 2x going to get? X squared. And we would put plus c if it were indefinite, but it's not. It's definite. So he's got x squared, and he's going to evaluate that thing starting at 2 and going to x. And then remember what we do with that. We take capital F of my upper bound minus capital F of my lower bound. Then I plug it in. I take x, I plug it in. So x squared. I take 2, I plug it in. Minus 4. Done. X squared minus 4 is my first answer. Everybody go on the first one. Fairly straightforward. Second one. Okay. And we can mess with bounds, but let's just leave it for right now. We're finding the antiderivative. It's the same one as the last one because it's the same problem. This time I'm evaluating from x squared to 2. We're doing capital F of 2 minus capital F of x squared. I plug in. 2 squared is 4. Sorry, trying to color code. 4 minus, I take x squared, I plug it in, I get 2x squared. Everybody good? That's it. That's all we learned on Friday. We took the antiderivative, we plugged in upper and lower bounds. Now we're going to do something beyond that today. Yes, sir.
How did you get the second one again for the right bound? Yeah, wouldn't x squared is the second?
I'm taking x squared and I'm plugging it in there. Oh, geez. Yeah, my fault. Just kidding. I'm plugging it in there. Man, I just want to make you think. I want to make sure you're locked in on a Monday. You're locked in. I knew I was doing it weird. My bad. I meant to plug into x squared. All right. So I get x to the 4th. Everybody good there? All right. Cool. Today we're going to add a layer to that. So today what we're doing is we're going to have that same problem, but then we are going to take the derivative of that integral. Okay, we're going to take a derivative of an integral. How do you think derivatives and integrals are related to each other? They're kind of opposites, right? They're kind of opposites. So look what happens. We could do the integral just like we did. Boom, 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 boom. We get x squared minus 4. Then let's take the derivative of that. What is the derivative of x squared minus 4 going to get me? Look at this. We got 2x here. Guess what we started with? 2x. Because we took the derivative of an integral. The ideas cancel each other out. It's like if I took 4 and I squared it, but then I square rooted it. Well, yeah, it would be 4. Okay? Because they are opposites of each other. They would cancel each other out. And that's something we're going to do a lot of today. Derivative and integral, okay, it's just whatever function is given. Not always true, though, because look at this second one. We take the derivative of this integral. So I'm taking the derivative of this guy. What's the derivative of 4 going to get me? 0 derivative of negative x to the 4th would be negative 4x cubed. That is not the same thing we started with. Okay? And the reason for that is because it didn't have just an x. On this one, it was easy. It was just x. On this one, it was x squared, but it was on bottom. Okay, let me show you maybe a little bit different way of setting this one up. Imagine we flipped the bounds and we put that x squared on top. Well, what would allow me to flip the bounds and put x squared on top? Making it negative. So if I threw a negative out in front. Here's what we're going to learn today. If we are taking the derivative of this, you take your upper bound. You want to make sure your x is in the upper bound, but if x is in your upper bound, you take the upper bound, you plug it in. So I'm plugging in that upper bound of x squared. And then I'm going to multiply by the derivative of whatever I plugged in. What is the derivative of x squared going to get me? 2x. Guess what happens when I multiply all that together? Negative 4x cubed, which is the same as that guy right there. That is what we're learning today. You could do it by hand like we did here, where we found the antiderivative, plugged in, and worked through it. Or we can use a shortcut that would make this a little bit quicker. But that is called the fundamental theorem of calculus. That is where we're headed today. All right, here we go. If f is continuous on an interval, okay, and capital F of x is equal to an integral, the derivative of that integral is going to just be f of x. Basically, if you take the derivative of the integral, the two things are going to cancel. That alone is pretty easy. Now, that is only true if your upper bound is just an x. If your upper bound is just an x, when you take the derivative of the integral, they cancel each other out. It's just whatever is given. Okay? That's what we're going to try to work through, and we'll show you some different things. Let's put it into practice. Again, this is called the fundamental theorem of calculus, part 1. Let's do it. The derivative of this integral. So we're going to do it the long way and then not do it the long way anymore. First thing we would do is find the antiderivative because I'm dealing with an integral. Evan, what's the antiderivative of t squared going to get me? Add 1 to my exponent. So what's my new exponent going to be? 3. And then what's my new leading coefficient going to be? 1/3. Good. Add 1 to his exponent, divide by his new exponent. Good. That's my antiderivative. He is then going to plug in his upper bound, or his lower bound, upper bound minus his lower bound. So it's going to be capital F of x minus capital F of negative pi. And so if we did that, it would be 1/3. Take x, plug it in. X cubed minus 1/3 negative pi cubed. It's some number, but I don't really care. I'm just going to leave that for right now. But that's not what the problem asks us to do. The problem asks us to take the derivative of this integral. So I still need to then take the derivative of this integral. What am I going to get if I take the derivative of 1/3 x cubed? X squared, because remember we multiply by my exponent and then subtract 1 from my exponent. It's x squared. What is the derivative of negative 1/3 negative pi cubed? Nothing, because all of that is just a constant. That is my answer, x squared. Well, hey, we kind of knew that already. I was taking the derivative of an integral. Okay, derivative and integral are opposites of each other. If x is in my upper bound, all I got to do is plug it in. That's my answer. It's just x squared. Anybody following me a little bit? I know it seems kind of weird. We're trying to look through a shortcut. You can do the long way every time if you'd like. Shortcuts are nice. Let's look at number 2. Find dy dx if y equals 1 x squared cosine t dt. Okay, so we're finding the derivative if we're given this. So the first thing I'm going to do is find the antiderivative of that. I got cosine t. So A and H, what's the antiderivative of cosine going to get me? Sine. What comes before cosine? It would be sine t. We would go plus c, but we got bounds. So we're going to go with bounds. 1 to x squared. Finish that problem, see what you get. We're finding the antiderivative, or we found the antiderivative. We're plugging in upper bound, we're plugging in lower bound, so it's sine of x squared minus sine of 1. Then we need to take the derivative of this guy, dy dx of that thing. What do I need to do to take the derivative of sine x squared? Chain rule. That is a chain rule question. Okay? It is a chain rule question. So Slade, what's the derivative of sine going to get me? Cosine. And then you are going to rewrite your baby, so x squared, times the derivative of our baby. So what am I going to multiply by? 2x. Then I'm taking the derivative of negative sine 1. What is sine of 1? It's a constant, and so the derivative of that constant goes away. This is my answer. Obviously, I'd rather write it with the 2x in front. But that is my answer. Again, we did it the long way. You don't have to do it the long way. Here is the shortcut way. If you're taking the derivative of an integral, if x is in your upper bound, you take it, you plug it in, just like we did, and then you multiply by the derivative of whatever we plugged in. We plugged in x squared, so we multiplied by 2x. Okay, that is the quick way of doing this problem. Okay, that's going to be kind of the better way of doing it. We do it faster. Let's look at example 3. Example 3, we are finding the derivative of an integral. Those two things are opposites. If x is in the upper bound, all we have to do is plug it in. Is x in the upper bound? Cool. Plug it in. So I'm plugging it in there, and I got to plug it in there. So my answer is going to be x over 1 plus x squared. If I plugged it in, then I got to multiply by the derivative. What's the derivative of x? 1. So you could do like x times 1. No, it's just x. And I plugged in x here. Oh, it's times 1 again. Boom, that's my answer. Done. That is the derivative of the integral. It was just x. And since the derivative of x is just 1, it's super easy. Questions on 3? Yes, ma'am. Nope, because you just take the derivative of whatever you plugged in. Since we plugged in x, that's the only thing we had to take the derivative of. So I plugged in x, I took the derivative of x, which is 1. I took the derivative of x, which is 1. Okay, if I plugged in x, if I substituted in, like on this one, I substituted in x squared. So since I substituted in x squared, that's why I had to multiply by 2x in the end. I didn't have to multiply the first one by a derivative because it was just x, and the derivative of just x is 1. Okay? Let's go with example 4. Try that one with your neighbors. See what you can do. Go. Here we go. Derivative of an integral. So if we're taking a derivative of an integral, we want to make sure that x is on top. We're good there. Okay, so Dylan, what'd you do with that 3x squared? You're going to plug it in. So we get e to the 4 times minus 6. He's plugging it in. So he's plugging in a 3x squared. And then you're going to multiply by that derivative. What is the derivative of 3x squared going to give me? 6x done. Nope. I mean, we could. It'd be 12. You just want it in the upper bound. If it's in the upper bound, we can plug it in. Let's go to the next one. Here's something they've been doing lately on this part. So pay attention to this. They've been doing this quite a bit lately, so follow along with what we're saying. They will say, like, find dy dx given, let's do a different one, y equals 2x plus the integral from 0 to 2x, 5t minus 9t cubed. So I added a little bit more. Instead of just the derivative of an integral, it's the derivative of this whole function. Okay, it is not that much harder, but kids just forget about this part in particular. Don't forget about that part. If we are taking the derivative of this whole thing, we got to take the derivative of 2x. What is the derivative of 2x going to get me? 2. Okay, so the derivative is going to be 2 plus the derivative of this thing. Well, now I'm taking the derivative of an integral. So if I'm taking the derivative integral, I'm going to do the same rules I've been doing. What am I going to do with this 2x? Plug it in. Plug it in. So 5 times 2x. And then I'm going to multiply by the derivative of the 2x that I plugged in. What's the derivative of the 2x that I plugged in going to be? Oh, t to the 5th. My fault. Oh, man. I'm struggling. Let's try that again. Let's act like it said t to the 5th. Same idea, though. I plug in 2x to the 5th power, and then I got to multiply by the derivative of what I plugged in. What's the derivative of what I plugged in? 2 minus 9 times whatever I plugged in. So 2x cubed times the derivative of whatever I plugged in. What's the derivative of what I plugged in? 2. I have to do it twice because I plugged it in two separate parts. But that's my answer. Questions on 5. One more. Look at number 6. What do you not like about number 6? It's on bottom. We can't do it when x is on bottom. So what we would have to do first is rewrite that thing. So this is the same as dy over dx. I'm going to flip it and put the 3 on bottom and the x to the 4th on top. T to the 1/2 power. I don't like square root. dt. What else would I have to do if I'm setting it up that way? Make it negative, because I flipped the bounds. I'd make it negative. Go ahead and get an answer. Go. Here we go. So we're setting that thing up. I'm plugging in. I'm derivative integral. X is on top now, so I plug it in. So x to the 4th to the 1/2 power is really the same thing as x squared times the derivative of what I plugged in. 4x cubed. Don't forget about your negative. And so in the end, my answer is negative 4x to the 5th power. I add exponents when I'm multiplying. That is my answer. It's a weird concept. It is not something we're going to do very often. Okay, most of the time when we take the derivative integral, it's going to be pretty easy. But every once in a while, they'll slip in a multiple choice question where it's a little bit strange. Okay, don't let it be that bad. Questions up until that point. The rest of this is not tough either. Okay, that is way more difficult than what we're about to do, at least in theory. Let's look at this next part. This is going to be what happens a lot more, especially in free response portions. F of x, capital F of x, is that guy right there. Then they're going to ask me different questions. For example, the first one, find f of 0. What do you think I'm going to do if I'm finding f of 0 here? Plugging in 0. Plug in 0 for what? X. That is an x value. It's f of x, so it's f of, that's an x value. So I'm going to plug in 0 for x. 2t squared minus 2 dt. I am finding the area under the curve starting at 0 and going all the way to 0. What is the area under the curve going to be if I start at 0 and I go to 0? Done. That one's easy. The second one says find f prime at 0. I don't know what f prime is. They told me f. So what am I going to have to do with f here if I want to answer questions about f prime? We got to find the derivative. So first thing I'm going to do is find f prime of x. I'm going to find the derivative. I am finding a derivative of an integral, so I got to think about that. What do I do to find the derivative of this integral? Plug in x. And then multiply by the derivative. Oh, it's just 2x squared. That is f prime of x. Anybody go to that point? That is f prime of x. Now what we're going to do is find f prime at 0. Show me with your fingers. What is f prime at 0 going to get you? Negative 2, because I'm just plugging in 0 here. 2 times 0 squared minus 2. Oh, it's negative 2. If I found f prime at 3, 2 times 3 squared minus 2. 3 squared is 9, times 2 is 18, minus 2, 16. Questions on 7. Just a matter of what did they give me. Okay, if they told me f, then I just plugged it in. If they wanted f prime, I had to take the derivative first. Let's go to the backside. On the backside here, same idea. Okay, we are taking this thing times that. We're finding g of 0 and g prime at 1. Go ahead and do that real quick without me helping you. See what you can do with it. G of 0 and g prime at 0. Remember, when you say you're multiplying by the derivative of what you plugged in, you're multiplying the whole thing by the derivative of what you plugged in. Keep that in mind as you go here. Go. Let's do it. Let's look at the first one. We're finding g of 0. So g of 0 is easy because they told me what g was. G of 0 just means I'm plugging in 0 for x. What is my answer going to be on this first one? Show me with your fingers. G of 0 is going to get you 0 because you're finding the area of the curve starting at 0, going to 0. Done. Then I'm finding g prime at 1. If I'm finding g prime at 1, the first thing I got to do is find g prime at x. So if I'm finding g prime of x, Michael, what do I need to do? Plug in x squared. Take that, plug it in. And so it is this thing cubed plus 3, but he's plugging in x squared. Plugging in x squared, and then he's got to multiply the whole thing. Not just the little part, but the whole thing by whatever he plugged in. What do you got to multiply that by? 2x. That's the derivative of x squared. Okay? Now we're finding g prime at 1. So if we're finding g prime at 1, it's 1 squared times, or 1 squared cubed. So it's 1 plus 3 times 2 times 1. 1 plus 3 is 4. Square rooted is 2 times 2. My answer is 4. Questions on that one? All right. Let's go to the next one. We are just Yes, ma'am. Yeah, I should have done a better job of explaining this. I knew someone. That's a good thing that you asked. It was all of this times 2. I distributed that 2. It's a great question. I should have been clearer when I did it the first time. That's why each thing had a 2. It's because I distributed it. Let's go to the back side. There will be a free response. This right here, I guarantee you, this is going to be a free response question in May. Okay, we are really good at graphs first semester. Okay, there was one on our final, and you guys did great on it. This is the wrinkle that they will throw at it that will make it a little bit harder. Okay, the graph of f of x is shown. So this is a graph of f of x. Just like always, when I see that, I'm going to highlight it, underline it, circle it, whatever you need. The problem with that is it is a graph of f of x, but what are they asking questions about? A. And so they're giving us f, but they're not asking anything about f. They're asking about a. So our job is to say, all right, this is a graph of f, but that doesn't help me. I want to know what are these graphs in terms of a. So how is f related to a? It is the integral of it. Okay? Or in other words, I always just draw this little silly picture. But I got f of x. If I find the integral of that thing, if I go back a step, it will tell me a of x. So that means if I took the derivative of a of x, it would get me f of x. So what else could I label this a graph of? This is an A prime graph. That is super important. Label that graph in terms of what they're asking. They are asking for A stuff. So I would much rather this graph be a graph about A. This is an A prime graph. So I'm going to find A of 2. I'm going to find A of 3. A prime at 2. And A prime at 3. All right, so we've got that information. Let's go ahead and do that now. We're going to find A of 2. Well, we could use the graph, but they also told me this right here, that A is this guy. So A of 2 is equal to the integral starting at 0 and going until 2, because it's A of 2 of f of t dt. So what am I looking for on that graph if I want to find the integral from 0 to 2 f of t dt? Area under the curve, starting at 0, going to 2. Show me with your fingers. What's that answer going to be? It's 4. 1, 2, 3, 4. Starting at 0, going to 2, it's 4. So A of 3, that's not any harder. A of 3 means I'm going from 0 until 3. I'm finding the area under the curve starting at 0, going to 3, f of t dt. What is the area under the curve starting at 0 and going to 3 going to get me? 6.5, 6.5, 1, 2, 3, 4, 5, 6.5, 6.5. That's easy. A prime at 2. That's an easy question too. Okay. Once we have labeled this as an A prime graph, this question is easy. A prime at 2. I've got an A prime graph. Show me with your fingers. What is A prime at 2 going to be if this is an A prime graph? It's 2. Because all that means is I'm going to this graph to where A is 2. What's the Y value? It's 2. Done. Let's turn it up a notch just because we could. What if I asked for A double prime at 2? What would A double prime at 2 be? Nah. It is DNE. Why does the slope not exist at 2? Corner point. We can't find the derivative at a corner point. What about A prime at 3? Show me with your fingers. What's A prime at 3 going to be? A prime at 3 is 3. What if I were mean and said A double prime at 3? What would A double prime at 3 be? It'd be 1. What would I be looking for on this A prime graph to talk about A double prime? Slope. The slope is 1. I'm up 1 over 1. Makes sense on that one. That one's a tougher one. As we get to it, we'll do more of that next chapter as well. We're putting our toe in. Let's go to the next one. Last one of the day. Okay, the graph of f is shown. So this is an f graph. H equals the integral of f. Or in other words, if you have f of t, and I found the integral of it, the antiderivative, that would tell me h of x. So what else could I label this a graph of? This is an H prime graph. Do that because every single question is about H. You want your graph to be in terms of whatever your questions are about. They're all asking about H, so make it in terms of H. This is an H prime graph. Does h of x have a local maximum at P? Talk with your neighbor. Come up with an answer. Thumbs up. It has a local maximum. Thumbs down. It doesn't. Nah, it does not. H prime has a local maximum, but H doesn't. What is this what is P actually going to be for H? H prime has a local maximum. That would make it a point of inflection. Good job. It is point of inflection. It's been a minute since we've done that. We'll come back to it. Talk with your neighbor. Where does H have a local minimum and a local maximum? Where does H have a local min and max? Talk to each other. Come up with a spot. Give it a reason why. Show me with your fingers. Where did we have a local maximum? Show me with your fingers. Where do you have a local? I'm sorry, local minimum is what the first one. Local minimum. Where do I have a local minimum? Oh, I'm seeing some R's, some S's. Local minimum is going to happen at R. Somebody raise your hand and tell me, why is there a local minimum at R? H prime changes from negative to positive. That is where maximums happen. When H prime or minimums happen. H prime changes from negative to positive. That's a minimum. So when am I going to have a local maximum then? At S, because H prime changes from positive to negative. You can't talk about H prime. If this were a free response question, you can't talk about H prime unless you've labeled. Okay, unless you've said that, hey, that's a graph of F, which really means H prime. That's important. Last one, and we struggle with this one. Talk with your neighbor for a second. True or false? H of x is less than 0 for all x's in the interval shown. Talk with your neighbor. Come up with an answer. Let's see. Thumbs up. You think that's a true statement. Thumbs down. You think it's false. Thumbs up if you think it's true. Thumbs down if you think it's false. Oh, no. Oh, no. Oh, no. It is true. It's true. Let's talk about why that's true. H of x is less than 0. In other words, h of x is negative everywhere on the graph. Okay? What am I doing? What am I looking for on this graph to talk about h of x? Area. Area under the curve starting at 0 and going to some x value. Okay? So let's say I went from there to there. So from 0 until p. Is the area negative? Yeah, it's below the x-axis. Give me a number for that. What would you say the answer is right now? Negative 4. Everybody cool with me on that? So let's keep going. Let's go till Q. What now do you think the area under the curve is?
Negative 4.
Is it more or less than negative? It's negative 8. Right? Because I'm starting at 0. I have negative, and then I have more negative area. Okay, if I kept going. If I go to R, now what would you say the area under the curve is? Like negative 10, negative 11. Sure, it's something more negative. It's getting more negative because I'm adding more and more negative area. Then we got this little guy right here from R to S. Oh, isn't that cute? What is my area under the curve going to be at S right now? Guessing. Something a little bit less than what it was, but it's still negative because we had way more underneath than above. Yes, ma'am.
So we can't just say like it's false because from R to S it's positive?
No, because we don't start from R to S. Every time we look at area under the curve for H, we're starting at 0. Okay, so because we're starting at 0, that's why the area is always going to be negative. And then obviously here at the end, we would get more negative.